Okay, in this video, we'll begin to look at the convergence of a series. Now, in the last videos, or set of videos, we looked at the convergence of a sequence, and let's take a look and give it a little bit of an introduction to what both these two things are. Now, first of all, we'll talk about sequences and series. And from the last video, you may remember that a sequence converges if the last term in the sequence approaches a constant. And to show that, we did this right here. We found that the limit as n approaches infinity of a sub n is equal to L. So as n goes way off to infinity, if the last term in the sequence seems to be approaching some fixed number, then the sequence converged. And what we get this time, all a series is the summation of a sequence, so it would look like this. So a corresponding series would be, if you had a sub n, if you take the summation, the partial sums of the sequence, as n goes from 1 to infinity, if this sum also approaches a fixed number, then you'll be able to say that the series converges. So last time we did sequence converging, this time we did series converging. Now to do this, we're actually going to look at it from a point of view of graphically. There won't be a lot of math in this. We will look at partial sums and actually introduce something called the nth term derivative test, or test for the nth term test for convergence, or actually divergence. And let's see here. Now, as far as the two examples we use will be this. The first one is going to be sequence will be 1 over n squared. The second sequence is going to be 1 over n. Now, the reason I picked these two, these will show up a lot. Surprisingly, these things show up all the way through your investigations of sequences and series. The sequence 1 over n has a name, and it's called a harmonic sequence. So we can go ahead and put that here. So 1 over n is the harmonic sequence. And let's try these. Now, what we want to do in this case is to investigate what does it mean for this series to converge. And we'll actually begin with this one, 1 over n squared. So let's take a look at this, and then we'll run through some examples. Okay, now in this first one, it looks like this. If you have the sequence 1 over n squared, if you wrote it out in its expanded form, you would have 1 over 1 squared, which would be 1. 1 over 2 squared is 4. 1 over 3 squared is 9. 1 over 4 squared is 16, and so on. So this is what it would look like. Now, we'll have two graphs here. On the graph on the left, this will be the graph of the sequence. The graph on the right is going to be the graph of the corresponding series. So first of all, to plot that, if I were to just come in and plot these points, I would have the point 1. And so when n is equal to 1, this thing is equal to 1. So I'd go 1, 1, and I'd actually have a point right there. If I had 1/4, when n is equal to 2, I'd have 1/4. And I'll go ahead and just put these up here for you. But if you plot them up, they would look like this. So 1/4 is right here. 1/9 is right here. 1/16 is right here, and so on. And it goes on out to 10. Now, first of all, if you look at this, you might remember from our last set of videos on the convergence of sequences. If you just look at this, it does seem to be converging. So the idea is, if you go way off to infinity, this series of blue dots seems to be approaching 0. So it seems like it's coming all the way in here, and it seems to be approaching 0. So we could actually write it, I think, and we'll put it like this. We'll put it in red here, and we'll make this would be saying that the limit of this sequence as n goes to infinity is approaching 0. So the sequence is converging. Now, that's just the graph of the sequence. Now, to do a graph of the series, what the series is nothing but a series of partial sums of the sequence. So we'll kind of write it like this. For this case, this will be the series is the summation of the sequence as n goes from 1 to infinity, and that's going to give you the series. So we'll put the numbers of the series right here. Now, how do you get these numbers? Well, they come from something called a partial sum, and let's go ahead and we'll put that over here. So we're going to try to find a partial sum, and the terms of the series are nothing more than the partial sums of the sequence. So we can write it like this. S1. The first sum is just when n is equal to 1, you're going to have 1. So the first term in the sequence is the same thing as the first term in the series. So this would be 1. Then to find the second partial sum. So the second term of the series is just these two terms added together. So it would be 1 plus 1/4. And if you added that together, you would get 5/4. So the second term of the series will be 5/4. Let's get the third term. So the third partial sum would be just the first three terms added together. So this would be 1 plus 1/4 plus 1/9. And if you added all those together, you would get 49 over 36. So the third term of the series is 49 over 36. And that's nothing but these first three added together. And we'll do one more. The fourth partial sum would be 1 plus 1/4 plus 1/9 plus 1/16. And if you added all those together, you would get 205 over 144. And that's going to be the fourth term of the series. So 205 over 144. And then you could go on for, we'll put three little dots and off you go forever. So they look like that. So what this is the series. So if the blue numbers up here are the sequence, then these red numbers are the series. We might put a little thing right here and call this just a reminder. This is the sequence, and this one is the series. Okay, now if we were to plot these, and I think I'll just go ahead and put them up here. If I were to plot one, let's see, and we'll put them right. Now let's go ahead with this. If when the first term of the series is equal to 1, I have 1 and 1, and I'd have a point, say, about right there. Now, if I were to plot 5/4, then it would be 1.2, and I'll go ahead and just put all the rest of these up there. It would look like this. So when n is equal to 2, you'd have 5/4, and it would be this point right here. When n is equal to 3, you would have 49 over 36, which would round up and be about this point right here. 205 over 144 would give you this point right here, and so on. And when you did the series, you would come up with this series of blue dots right here. Now, another way of doing this, I think I'll just give you a quick example right now. If you graphically do these things, and this is kind of a quick way of doing them, if you've got the graph of the sequence, you can get the graph of the series by doing the following. Now, the first point on the sequence is going to be exactly the same thing as the first point in the series. So you'll have this height right here is exactly the same as this height right here. And you get the first point. Now to get the second point, you're just going to add this height to this height. And one way of doing that is to just come straight across from here and just take this height right here and add it on right here. Then to get the next point, you'll just add this height to this height. So you can come from here across, go straight up, and you've got that height. Then this next height, go right across, go straight up that little distance, and you'll have that one, so on. But just keep going like that. And it's a quick way of, if you've got a sequence, to sketch a quick graph of a series. Okay, so that's just a little side thing. Okay, now what this one means is, let's take a look at this. The question is, here is a sequence, and let's go back to this, and we'll put it in, I think, black right here. The question is this, is the sequence converges because the terms of the sequence are approaching a fixed number. Now, a series converges if these blue dots also seem to be approaching a fixed number. And in this case, I think I'll go ahead and put it in red, these blue dots seem to be leveling off at, and it's going to be somewhere approximately right here. So say from here over to about right here. So what happens is this thing is going to be S. So the sum of all these little blue dots seem to be leveling off, and they seem to be approaching this. Now you can kind of look at it, it's a little bit more than 1.5. Let's just say it's approximately 1.6. So what this means in this particular example, that the series is converging, and it seems to be converging to 1.6. So this right here, you can come up here and say it seems to be converging. So we'll just put the series converges. And it seems to be converging to about 1.6. So in this case, and I think I'll write it down here, this would be saying that the summation as n equals 1 to infinity of the series is approaching S. And going back up to our original thing, let's put both these back up here again. Again, the sequence converges if the terms of the sequence are approaching some fixed number. The series converges if the series are also approaching some fixed number. That's sum. And that's what's happening in this case, is the series graph is leveling off. It seems to be leveling off and not going to go above about a 1.6. So in this case, the series does converge. Now that's 1 over n squared. Now we'll do, in the next one, we're going to do 1 over n, and it'll be very similar, but the results will be somewhat different. So let's take a look at that. So again, this one was a sub n is 1 over n squared. This next one's going to be 1 over n. And what it looks like will be this. So this time, if you have 1 over n, now we'll do kind of exactly the same process. Starting with 1 over n, if you wrote it in the expanded form, it would look like this. So 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, and so on. Now, again, the sequence graph will be on the left, the series graph is on the right. So if you wanted to plot the sequence graph, and let's just go ahead and do that, if I were to plot these, they would look like this. So here is 1, here is a half, here is a third. And what they seem to be doing is this. Again, just like in that last example, they are decreasing. They seem to be approaching the x-axis. So again, I'll kind of make the claim here, and we'll put it in green, that the limit of this sequence as n approaches infinity seems to be approaching 0. So again, the green dots are getting closer and closer and closer to the x-axis. They seem to be approaching 0. So in this case, the sequence converges, and it converges to 0. Now we'll do exactly what we did last time, is let's go ahead and get the partial sums of this thing. So what I'd like to do, and I think I'll do it again, and we'll put it in black, I guess, this time. I want to come up with the term. So the first term, the first partial sum is going to be just 1. And here I'll write down the terms of the corresponding sequence. The second partial sum would be the sum of the first two terms. So 1 plus 1/2, and that's going to give me 3/2. So the second term is going to be 3/2. Then the third partial sum would be the sum of the first three. So 1 plus 1/2 plus 1/3. If I added all that up, I'd get 11/6. So the third term would be 11 over 6. And let's do one more. The fourth term would be 1 plus 1/2 plus 1/3 plus 1/4. And if I added all that together, I'd get 25 over 12. So the next term would be 25 over 12. And they would go on like this. Okay, now we'll still plot them exactly like we did last time. It's just if you plot these, we'll plot these will be the terms of the series. Now again, this one was the sequence. The first one was the sequence. So here are the terms of the sequence, and here are the terms of the resulting series. So if you were to plot these, and we'll just go ahead and do it real quickly, they would turn out to be these green dots right here. Now what happens is 1 corresponds to 1. Then if you were to take this height and add it to this height, you would get this height, and so on. And if you plotted the points, they would do this. Now there's a difference in what happened in this series and what happens in the last series. In the last series, when we plotted the blue dots, it looked like the blue dots were leveling off at a certain value, and it turned out to be about 1.6. And what you'll find, this is kind of hard to tell in this one, this is difficult to judge. It looks like maybe they're leveling off, but they're definitely going up a little quicker. But as it turns out, and you'll see this in later videos as we get farther into the section, that this thing never does level off. In fact, it actually goes all the way up. If you went far enough out, it would go off to infinity. So what this means is that on this one, the summation of the sequence as n goes from 1 to infinity, this thing does not exist, which tells you that the series is going to diverge. So if it doesn't settle on a fixed number, it diverges. And sometimes it's really easy to tell, like if it just took off and went straight up, you would know it diverges. Sometimes it looks like it levels off and you need to go way out to see whether it actually does or not. But in this case, just a little bit of a heads up on some future stuff. A harmonic series does diverge as you go off to infinity, way off to the right. Now again, a couple things to keep in mind, and I think I'll put both these on here. Let's take a look at it, and I'll flip back and forth between the two of them. So this is 1 over n, and it's the green dots. Then we had 1 over n squared, and it's these blue dots. So the blue dots look like this, and it levels off like this. Now look at the difference. The blue dots come down fairly quickly. The sequence comes down fairly quickly, and the series levels off and converges. But in the next example, the green dots also approach the x-axis, but they don't do it nearly as quickly, and in this case, the series diverges. It continues on off to infinity. Now, if we put both these on the same screen, let's just go ahead and do that. I'll put together here. The blue dots represent 1 over n squared, and the green dots represent 1 over n. Then on this one, the blue dots again represent 1 over n squared, and the green dots represent 1 over n. Now, the important thing to take away from this is in both cases, the sequence is approaching 0. So the blue dots are approaching 0 and the green dots are approaching 0. And this will pop up a lot, that not only if the sequence is going to converge, then the dots have to be approaching 0. Now, it'll turn out that not only do they have to be approaching 0, but they have to be approaching 0 at a certain rate. So what happens is the blue dots are approaching the x-axis at a fast enough rate that the resulting sequence, or the resulting series, levels off, and it seems to level off, we'll kind of put a line here, about right here, and it turns out to be about 1.6. So the blue dots are leveling off. Now the green dots, they are approaching the x-axis. They're being a little lazy about it. They're not getting there very quickly. And if that's the case, even though they're approaching the axis, the series never does level off at a constant. It goes on. So the important thing here is that the speed at which these things are approaching the axis makes a difference. Now, to introduce something called the Nth Term test for divergence, and it's based on this. What happens is, and notice what happens, let's kind of go over here, we'll put this thing back in red. Notice what happens as a sequence levels off. In other words, you go from here and you're going to increase by this much. In the next term, you only increase by this much. The next term, you only increase by this much. The next term, you only increase by this much. So each one of these little increases is getting smaller. Now, let's kind of run through it. This increase here would be this one right here. This increase right here would be this one right here. This little increase right here would be this one right here, and so on. So if the series is going to level off, then the terms that you're adding to it have to be getting smaller and smaller and smaller. So these little things have to be approaching 0. And since these increases are the same as these numbers over here, if the series is going to converge, it can only converge if the terms of the sequence are approaching 0. Now, if the terms of the sequence are not approaching 0, then there's no way that the series can converge. It's able to take off and head off to infinity, or maybe oscillate between some points. So again, if the terms of the sequence are not approaching 0, then the series must diverge. And we'll go ahead and take a look. That's actually the definition of something called the Nth Term test for divergence. And it looks like this. It says, if the limit of the sequence, if the terms of the sequence are not approaching 0, then the resulting series must diverge. And that, again, is nothing more than this thing right here. So if the terms of the sequence are not approaching 0, it has to diverge. Now, there's another thing some students will try to do, so let's go ahead and put this up here right now, is that it's tempting to say this: if the terms of the sequence are not approaching 0, then the series diverges. And it's very tempting to say this, and we'll go ahead and put this in red here. So what happens if the terms of the sequence are approaching 0? Let's go ahead and we'll put it right here. So suppose that the terms of the sequence were approaching 0. So if the terms of the sequence are not approaching 0, you know it diverges. But if the terms of the sequence are approaching 0, it's tempting to say, well, in that case then, surely it would converge. But the trouble is, this is not true. So if you know that the limit of the sequence is not 0, you're guaranteed it diverges. But going the opposite is not true. But what is true is this: if the limit of the sequence is approaching 0, you can do the following. All that means is that the nth term test is inconclusive. So inconclusive. And then basically try another test. So try another test and see what happens. So again, if the limit of the sequence is not 0, you know it diverges. But the limit of the sequence is 0, that does not mean that it converges, it just means that you have to try another test. Now an example of this would be this. Actually, let's look back at these because you'll see where this comes from. So 2 cases where the limit of the sequence is equal to 0. Let's look at the first example. In the first example, in this case, the limit to the sequence, we'll put it right here, the limit of the sequence was 0. This thing was getting closer and closer to 0, and the series converged. But in the second example, you had sort of the same thing, is, again, the green dots were getting closer and closer to 0, so the limit of the sequence, again, approached 0, but in this case, you had these green dots here, and it diverged. So just because the sequence is approaching 0 doesn't necessarily mean that the sequence itself will or series itself will converge. Maybe it'll converge, maybe it will not converge, and that's where this nth term test comes from. So again, if the terms of the sequence do not approach 0, you're guaranteed it diverges. That makes a quick check just to see whether something diverges or not. But if they are approaching 0, then the best you can do is say, well, the test failed, I'll try another test. And again, this is just a quick way of checking for divergence, and that's what we'll actually do working some problems in the next example. So this video was just to show you kind of graphically what all the different terms mean.